Alright, so this is our video on 2 more tests to add to the ones that we have, and this is for comparison of series. So we'll have 2 different ones, direct comparison and limit comparison. And so we'll talk about both of them and when you would choose to use them. So make sure you're really paying attention to all of that because again, the more and more tests we get, the more we need to start paying attention to how I know which one to use at what point. So the first one we're going to do is important because of the concept of it, is to understand how we can compare things. Now we kind of did this with integration to be able to compare to see whether integrals converged or not. So it's actually very similar to that. I will tell you that this test, and when we get to the page, to the part where it writes it down, this would be the last test I would normally ever use. Now I say that, and I'm going to say it multiple times in this video. I say it in class over and over again, and then I still have students that'll take a test and try to do direct comparison on the entire test. And it's literally the last thing I would ever use. And it's really only a test that's going to work if I'm comparing 2 things like what are written. So they're almost the same thing, they just differ by a tiny little bit. Otherwise, it's extremely difficult to use. Okay, so it's not something that we're going to use often. Okay, so we're going to write out the first terms of the series if an equals 1 over 2 to the n and bn is 1 over 2 to the n plus 1. So first terms, if we just plug in 1, we'll get 1/2, and then we'll get plus a 4th, plus an 8th, plus a 16th, plus 1 over 32. Well, if we do b sub n, we're going to have the same exact numbers, except you're going to add 1 to the denominator, because you're going to get 1 over 2 to the first plus 1, so that's 1/3, and so on. So it's very simple to write the terms down. It's just the one that was above it with one number being added to the denominator. Well, what that means is that clearly a sub n is bigger than b sub n for all values as long as we are from n greater than or equal to 1. And this is going to be important for us to compare things too. So let's think about it for a minute. So let's look at a sub n. Let's note that it's geometric. So since it's geometric, I would want to identify what r is. So for an, r is 1/2. You're multiplying by 1/2 each time. Well, we know that since that is less than 1, then this converges. And since it converges, we can find the sum. So they ask us to find the sum, which basically tells you it converges, but I still want to verify that. Okay, so definitely this converges. So I want to find the sum. So the sum is the first term, which is 1/2, because we have it written there, first term, divided by 1 minus the ratio, which is 1 minus 1/2. Well, 1/2 over 1/2 is 1, so the sum is 1. So with that knowledge, then what do you think would be true about the summation of b sub n? Well, we know that this series, every term is going to be smaller than every term of the other series. We can see that because of the way the denominator is. So that means this sum must be less than 1. I can't tell you for sure what it is, but by that method, but at least I know for sure every value is smaller, so the sum has to be less than that. Well, even more, what would be true is, since a sub n is basically bigger than b sub n, then it means I've got a series that's bigger, so further from 0, going to 0 slower, and it converges. So therefore, if something is got all terms that are smaller, that means it's going to 0 faster, so it would have to converge also. That was that idea that we used with integration. And I told you that would be important later, and here's where that comes up, okay? So here is the idea for how we know, and then we'll look at the test. Oh, where is the Oh, well, I guess there isn't a page on here, so I'll just add a page and write that or look at it. So the direct comparison test basically says if you have a series, so first of all, we have to know that A sub n is less than B sub n in this scenario, okay? So if that's true, then if the series B sub n converges, okay, so think about it again, the bigger one converges, so something with bigger terms further away from zero, going to zero slower converges, then it must be true that the A sub n one would converge, okay, that has to be true. And then also the other case would be if we know that the A sub n one diverges, okay, so again, the one that is smaller, so goes to zero faster, if it diverges, then certainly the other series that is bigger, it doesn't have a chance. So it's going to also diverge. Okay, so that's what it says. So then in thoughts, it's kind of like we had to do with the integration ones we compared to. So which again, we almost never used. We basically use that to show why it makes sense for things to converge and diverge, but then ultimately we learned how to do limits and do some things and figure it out on its own. Well, that's why it's kind of the same thing here. The direct comparison test would be sort of the last thing I would use. So you need to even write that. So on the part that I don't have on the screen, but it says direct comparison test and lists the test there in the about 2/3 down on your page, make a huge note and say, this is kind of the last thing I would ever use. And the only time I would ever use it is when it's super simplistic, like the first example that we did. That's really the only time. So same kind of thing though. If I think my series converges, so first we'll have to guess. Do we think it converges or diverges? If we think it converges, we got to compare it to another converging series. And then we need our series that we want to know if it converges to be smaller, because if the bigger one converges, and I can prove that one, then mine must. And then vice versa for the diverges, okay? So we're going to use that. So you'll notice that these series, when we do these 4 examples, are all very, very simple. They don't have a lot of terms. And really A and B, not C and D, but A and B would be about the only 2 that I would use this direct comparison test on, because they're almost exactly a P series or geometric. There's just a tiny little change. Otherwise, I would use the next test that we're going to do, which is called the limit comparison test. Now that one is much easier to use, and so we would use it more often. So first thing we have to do, if we're going to use a comparison test. So if I'm on homework or I'm on a test and it says use the direct comparison test, you have to use it. So we're going to use it on these examples. But then again, if I get to choose, I'm almost never going to choose that, okay? So here I know that's what I need to do. So the first thing I need to do is look at the series on part A here, and I need to figure out, do I think it converges or diverges? Well, what I'm looking at is, what I'm going to compare it to is the series where you basically get rid of any numbers or anything and just look at 1 over the 3rd root of n. So ignore the 7. So I'm going to compare it to that. Well, that series is a P series where P equals 1/3, right? Because this would be n to the 1/3 in the bottom. And 1/3 is less than 1, thus this series that I'm getting ready to compare to, okay, diverges, okay? So that means my guess would be mine diverges, okay? So now we have to think about it. So which way do we need an inequality to hold? Well, if the 1 over 3rd root of n that I'm comparing it to, if it is closer to 0 than my series and it diverges, then there's no way my series is going to converge. So what I need to be true is that the nth term of my series that I'm trying to prove must be bigger than the one I'm using to compare it to. Well, I can't just write that. So don't just write an inequality and just be like, well, that's true, because it's not always true. That's why this test is so hard. They have to be a certain way. Well, in this case, is this true? Well, the denominators are the same. On the left, you have a 7 for a numerator, and on the right, you have a 1. So clearly, the left number is bigger. So this is true. So this is true for n greater than or equal to 1. So I don't care what happens other places. I only care what happens where the series exists. And it is true here. So it could be not true other places, don't care. It's true here. And that's all that matters. So basically, I have found a comparison series. So step 1 is figure out what to compare it to and show that it converges or diverges. Second thing I have to do is show that the inequality is true. Okay? So when I compare it to something, I do have to state whether that comparison series works or doesn't work. I can't just compare it to something. So first thing I always do is show what the comparison series does, show the appropriate inequality, and then the last thing that I do then is I'm going to make my statement. Therefore, always write out again the original thing you're trying to prove. Therefore, this series diverges also by direct comparison test. Okay, so basically what we learn is they both do the same thing. That's why I like to use the word also. It reminds me I compared it. So the series I picked diverges, so this one does too. Okay, as long as I meet the criteria. All right, so let's do this other one. I'm going to actually move it on my screen here, but you have it in a separate box there. So we're going to try this one. Okay, so basically to choose what to compare it to, you just sort of ignore anything except the stuff that has the biggest powers and that kind of stuff. So I'm going to basically compare to, this is what I'm going to try. I may not always get the right thing, but I'm going to try to compare it to 2/3 to the nth. Okay, so ignore the +1. And if it had been 5 times 2 to the n, I would just use 2 to the n. So you kind of ignore everything except those big parts. So that's what I'm going to compare it to. Well, that series, I'm going to say, I'm going to compare it to that, which is a convergent geometric series for convergent geometric series because absolute value of r equals 2/3, which is less than 1. And remember, for geometric, less than 1 means converges because you keep multiplying every term by that 2/3, which means each term is getting smaller. And getting smaller is good for convergence, okay? So there's step 1. I picked a series to compare it to, and I've said that it converges. So that means I'm going to guess that my series converges. So if my series that I'm trying to prove converges, then I need to have an inequality between these two things. And I'm going to write this one as 2 to the n over 3 to the n just to make it easier to see. Well, again, I know the one on the right. I know that 2 to the n over 3 to the n. I know that series converges. So if my series is smaller, okay, then it must converge too. Because if a bigger one converges, the smaller one does. Well, this is really easy to see that this is true. You don't have to state any more than, yes, I see it's true, because numerators are the same and the denominator on the left is the same number plus 1. So it has to be smaller. Bigger denominator, smaller number. So this is true, again, for n greater than or equal to 1. It doesn't matter what happens if n is other numbers. I only care about what happens on the place that I'm doing it. So that's step 2. So the last thing is make your conclusion. So therefore, my original series that I'm trying to prove, okay, does the same thing. So that means it converges. So it converges also by direct comparison test. And I don't care if you go to a tutor, if you have a friend, whatever, that tells you, oh, you don't have to write out the words direct comparison test, ignore them and write them out, okay? No abbreviations, because you're running a lot of risk there, okay? So your hand is not going to fall off. You'll be fine if you write all those words out, okay? But if you don't write them out, you could lose all the points on the entire question because you didn't state the test. So let's don't do that, okay? All right. So let's look at the next 2 examples, and I'm going to just go ahead and move this one out of my way because I know I'm not going to have room. And then I guess if I make this bigger, actually, I'll have a little more room. So we're going to do this one. So again, if I'm going to use direct comparison test to do this, I need to figure out what to compare it to. So you ignore the -1 and the +3, and you look at n over n cubed. Well, that simplifies to 1 over n squared. So we are going to compare to the series n equals 1 to infinity. Now, if that had started at 2, I would start at 2, okay? You just make sure you start at the same place. I'm going to compare it to 1 over n squared. So that's how we get a comparison to try. Now, sometimes if you try the direct comparison test, you can't get the inequality to work that we're going to do in a minute. It's not true. If it's not true, then you can't use this test, okay? So that's the reason this test is very difficult. It has to have that inequality be true, and very, very often it's not. And so we don't actually, this is again the last test I would ever use, okay? Now, I'm going to go ahead and state whether this converges or diverges. So hopefully by looking at it as you're sitting here watching the video, you realize that that's a P series. So I'm going to say which is a convergent P series, comma, P equals 2. Remember, P stands for power. Power is 2, which is greater than 1. Now I've said everything I need to say. That comparison series converges. I've told you it was a P series, and I gave you the criteria. That's why I knew it converged. Okay, so again, remember, power being bigger means that the bottom is going to 0 faster. So that's why greater than 1 works. So that was my first thing. And you don't need to number these when you do them. I like to number them so it sort of visually helps you remember. There's 3 things. Show what the comparison series does. Second thing, the inequality must be true. So I have this term from what I'm trying to prove, and I have 1 over n squared. So I got to think about the inequality here. So my comparison series converges. So what I would love to be true is that the series that I'm trying to prove, again, is smaller in all ways than my 1 over n squared, right? Because if the bigger one, okay, 1 over n squared converges, then my series would converge, okay? So that's what I need to be true. Now this time I'm going to kind of put a question mark right there because I'm not actually sure. This one isn't super obvious because you can't just go, well, yeah, of course it is. No, I don't know that. So what we're going to do is we're going to basically cross multiply to get the inequality in a way that it's easier for me to verify that it is in fact true. So I'm going to multiply n squared times n minus 1 less than, and then I'm multiplying 1 times n cubed plus 3. So again, I still have a question mark. So now multiply out the left and leave the right. Is this inequality true? Well, it should be super easy to tell that as long as I start with 1, now it may not be true with a bunch of negative numbers, things like that, but it doesn't matter. I care about what's true when I plug in 1. Well, if I plug in 1, I'm going to get 1 cubed minus 1. Left will be 0. The right will be 1 cubed, and then I'm going to add 3. So if you think about it, this has to be true always, because on the right, you're adding a number, and on the left, you're subtracting a number, and they're positive. So therefore, it has to be true. So again, this inequality is true for n greater than or equal to 1. And again, only place I only care if it's true there. So that was my second thing I needed to show, was the inequality was true. So then the third thing is make my conclusion. Therefore, and I always write out the original series. Don't ever use a sub n or therefore it converges or anything. Always put the original so there's no confusion about what you're saying converges. And I would say it converges also by direct comparison test. Okay, so again, you have to say all of those words every time. And again, I like the word also because I'm comparing two things. So that does help me remember that they do the same thing, okay, once the comparison works. All right, so let's do this one last one, and then we'll do the easier test, the limit comparison test, which could have been used on really any of these, and we could have still gotten the answers, which is, again, why I would not use this direct comparison test very often. It would be my last choice, okay? So please don't be the person who gets on the test and tries to do direct comparison tests on every question, because probably none of them will need it, okay? Now, sometimes, again, it's quick. The first two examples, the direct comparison test is pretty quick. All right, so here, what we're going to do is, to find the comparison test, we're not only going to look at the highest powers, but I'm going to ignore the 8 over the 2, the 8 and the 2. So I'm really just looking at n squared over n cubed, which means that I am going to choose to try to compare to n equals 1 to infinity of 1 over n. If you simplify n squared over n cubed, you get 1 over n. Now, this is a series that I told you to memorize the name, because then it makes life easier. So I'm going to compare it to that, which is the Divergent Harmonic series. So we learned and I told you to learn it by name, because then I don't have to do anything except say it's the Divergent Harmonic series. Now, technically, you could also do, it's a P series where P is 1, which diverges. But since it's literally the harmonic series, that's all I have to say. Okay, so that's a fact. We don't have to do it again. We just say it's the Divergent Harmonic series. So there's my comparison series. So the series I'm comparing to diverges. So again, I have to figure out this inequality. I have to figure out which direction it should go. So the comparison series diverges. I know then that means probably mine diverges. So my series needs to be bigger, because if a smaller series diverges, then one that has bigger terms is going to diverge. Okay? So again, question mark, is this true? So do your cross multiply thing again. This time I'll go ahead and multiply it out. So I would have 8n cubed plus n. Is that in fact greater than 2n cubed minus 1? Well, that's super easy to see that as long as we're at n greater than or equal to infinity, clearly the left is larger, because you're going to have 8 times a number plus a positive number, and the right-hand side has 2 times that first number, and then subtracting something. So clearly this is true. This inequality is true for n greater than or equal to 1. So I've now proven that my inequality is true. I'm comparing it to a divergent series with the correct inequality. Therefore, my original series, which again, always write out the whole entire thing, diverges, because they do the same thing, diverges also by direct comparison test. And please do not practice on your homework abbreviating and think that you will remember on the test to do the right thing. Because I had a couple of people that abbreviated stuff that I'm going to take points off if you do that. Okay, so they did it for some other things, for like L'Hopital's rule. So don't do that. Just write it out. Not going to hurt you. You can do it. It's not that big of a deal. Okay, so then the next thing talks about how it can fail. We're going to actually skip that. Just know that, again, if the inequality isn't true, it doesn't work. Now, limit comparison test. Okay, so this is a test I would actually use. The difficulty is, just like everything else, I can only use it under certain cases. So I can only use this if my series have positive terms. Okay, so next section we're going to learn about alternating series where some of them are negative, and anything could have negative terms, of course. So disadvantage, I can only use it if it has positive terms. The other thing is I have to figure out a series to compare it to, and that's not always easy. So most often, I would even write this, most often you're going to use this when you have things that are rational. Okay, so if I'm doing a rational function trying to prove if one of my nth term is rational function, this is a really great test to use. Okay, limit comparison test. Now we're going to change this. Instead of saying L is 0 to infinity, we're going to say such that the limit is finite and positive. Now the reason I do that is because we have too many things that have inequalities and stuff. And all I care about is that when I get it, that I get an answer that's a number and it's positive. Okay? So as long as my limit is positive and it's not infinity, that's what finite means, not infinite, okay, that I'm good, okay? And so basically all we do, same thing we did on that test, we pick a comparison series, and then we simply take the limit of the ratio of those two tests. If we get a number answer that is finite and positive, so we get a positive number and we don't get infinity, then they both converge or they both diverge. So it's very similar, but much, much easier. I don't have to prove that inequality, plus direct comparison only works if that inequality is in fact true, which is not always the case. Okay, so let's do the limit comparison test, a much better one. So you're going to, again, the comparison that you're going to pick is virtually the same thing. And when we would mostly use it is if we have, again, something that's rational or rational-like, okay? Then I would choose, you ignore all the numbers and everything and you compare it to only the highest power terms and not the coefficients or anything. So like if we were going to do this one, we would compare it to 1 over n squared, okay? And then we would do this limit. So let's do that. So we're going to combine, and you're going to see this takes up way less room. Now still have to say what the comparison series does, that it converges or diverges, and then I just take this limit. If it's finite and positive, they both do the same thing. So this is again one I am going to compare to n equals 1 to infinity 1 over n cubed. Ignore all the numbers and everything and just pick that power. Okay? Well, we know that this is a P series where P equals 3, which is greater than 1, thus converges. Okay? So my comparison series converges. Okay? So that's step 1. Again, comparison. Second thing I need to do then is go ahead and take the limit as n goes to infinity of either one over the other. Doesn't make any difference. So I'm just going to write the 2 over n cubed plus 4 first. And then I'm supposed to put it over 1 over n cubed. But dividing by a fraction is the same as multiplying by its reciprocal. So we want to start with that. We don't want to take the extra work to do all of the other. Now, this limit is actually super easy because these are rational. That's why I was saying if they're rational functions, this is really simple. because you have 2n cubed on the top and you have n cubed on the bottom. And we know if we go to infinity that we simply take the ratio of that and we're going to get 2. Then I'm going to say which is finite and positive. Okay, because that's what we were told. Okay, if it's finite and positive, we're good. Well, 2 is a number. It's not infinity. That's what would be infinite. It's finite and it's positive. So therefore, my last step is simply to say, therefore, my original series, again, always write the original one down, 2 over n cubed plus 4 converges. Also, again, a comparison test. They do the same thing, and it converges also by the limit comparison test. Okay, and there you go. So much easier. I don't have to worry about the inequality. I literally just find something to compare it to that's a p-series or geometric, something like that, usually p-series. Do this limit. It's easily going to come out a number. Done. Okay, make my conclusion. All right, so let's do this one. So this one's even messier. So we look at it, and again, it's actually not that difficult to figure it out. So we are going to look at, we're going to compare it to this ratio, highest powered terms with no numbers in front, ignore those numbers. So we are going to compare to the series 1 over n. Okay, because it's n to the 4th over n to the 5th. So we're going to compare it to that, which we know is the divergent harmonic series. So I don't even have to do anything else. I know it diverges because it's the harmonic series, and that's a known thing. So there's my comparison series. So now I'm going to do my limit as n goes to infinity with my original nth term divided by 1 over n, which means times n over 1. Okay, because I just want to go ahead and flip, invert, and multiply. Well, again, I don't need to multiply it out to realize I've got n to the 5th on top and 4 n to the 5th on bottom. So that means my fraction, or my when I simplify my limit, because again with rational functions we just go to infinity, we're going to get a 4th, which is finite and positive. Now on your homework, if you practice every single time writing out those conclusions and really thinking about it, the tests are much, much easier to learn and remember. If you try to shortcut stuff and like you just don't want to write anything and whatever, you're just going to end up stressing yourself out. Write it every time. I got a number, it's finite and positive. My conclusion is therefore this original series diverges also, because that's the key. They do the same thing. Okay, it's a comparison test. So it diverges also by the limit comparison test. Okay, so much easier test. So again, limit comparison test. If you've got positive terms, do the limit comparison test. Direct comparison test, probably I would almost never use it. The only time to use it is when it looks like the first two examples, A and B, so it's really clear. And even then, it's not going to work every time because that inequality has to be true. So start with the limit comparison test at least. And again, a hint would be limit comparison test, very valuable when you have rational functions for the inside. So we have a rational type expression, then limit comparison test is probably a really good test to use. Okay, so that's it for these two tests. So make sure that you add them to your list of tests and that you practice really hard on the homework.